Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today, we're going to be tackling a practice problem set that relates to our lecture on bonding and chemical interactions. Let's go ahead and get started with problem number 1. Problem number 1 says, what is the character of the bonds in carbon dioxide? Are they ionic, polar covalent, nonpolar covalent, or coordinate covalent? Now, the way that this problem is framed is really important, and it might seem obvious right now as you work through this from the comfort of your home, but if you're taking an exam and this question pops up, you might skim it a little too fast and misunderstand it. This problem is asking us for the character of the bonds in carbon dioxide and not the character of carbon dioxide as a molecule. If you attempt to answer it in this alternative way, you're going to get the wrong answer. You're going to get a completely different answer. So I'm going to show you. I'm going to solve this problem for what it asks, and then I'm going to show you why, if you understood it in an alternative way, what kind of answer you would get and why you would get a completely different answer. So let's focus on the question at hand. First and foremost, this problem is asking, what is the character of the bonds in carbon dioxide? Well, carbon dioxide is a molecule that consists of one carbon atom and two oxygen atoms. Carbon dioxide is CO2. And the structure for carbon dioxide is as follows. You have an oxygen double bonded to a carbon and another oxygen double bonded to a carbon. And we're going to see that we actually have resonance structures for carbon here in a little bit. This is the most significant structure for carbon dioxide. Now, if you're looking at this molecule, you realize that the bonds in carbon dioxide are the carbon-oxygen bonds. And this problem is trying to ask us, well, what kind of bond is a carbon-oxygen bond? And for us to answer that, we would have to rely on the difference in electronegativity between these two atoms. Oxygen has an electronegativity of 3.5. Carbon has an electronegativity of 2.6. So all we have to do is take the difference. 3.5 minus 2.6 gives us a 0.9. All right, gives us an answer of 0.9. Now we can depend on our flowchart for bonding to figure out what that difference in electronegativity tells us about this carbon-oxygen bond. So let me remind you really quickly, a covalent bond results when two atoms share a pair of electrons. And you can have two subgroups of covalent bonding. You can have nonpolar covalent bonding, where this pair of electrons is shared equally between two atoms, or you can have polar covalent bonding where that pair of electrons is not shared equally. On the other hand, we also have ionic bonding. This is when the valence electron from one atom is lost to the more electronegative atom. And for each of these classifications, we have listed the criteria for electronegativity difference. Now, we just calculated an electronegativity difference of 0.9 between carbon and oxygen. This falls in the range that would classify it as a polar covalent bond. So the character of the bonds in carbon dioxide are polar covalent bonds. The correct answer here would be B. Now I want to show you how you would answer this question if it was asking you, well, what is the character of the molecule carbon dioxide as a whole? In this case, you would have to go through a couple of steps in order to be able to answer this. The first thing that you would have to do is draw the Lewis structure for carbon dioxide. Now, I drew the most significant structure above, but I want to work through this nevertheless. All right, our first rule for drawing Lewis structure is to account for our number of valence electrons, our total number of valence electrons. We get 4 from carbon and 6 from oxygen, but there are 2 oxygen atoms, so we have to account for that. That gives us a total of 16 valence electrons. Now we can move into the second rule for drawing Lewis structures, figure out our central atom. Here, carbon is less electronegative, so carbon is going to be our central atom. Then we can move into step 3. Now, there are 3 parts in step 3. Part A is to connect the bonds. We figured out that carbon is our central atom, so it's going to be connected to both of the oxygens. The second thing we want to do as part of step 3 is then complete the octet for the outer atoms. So we're going to go ahead and add enough valence electrons to these oxygens to satisfy their octet rule. We're going to have to draw 6 valence electrons for each oxygen. Now, if we account for all of the valence electrons we have drawn here, we have used and assigned 16 out of the 16 valence electrons we have. So moving into the last part of step 3, where we want to put any leftover electrons on the central atom, we recognize that we actually have no leftover electrons. Now we can move into our final step, step 4. This step is really important. This step says if the central atom does not have a complete octet, then you want to start to form double and triple bonds to make sure that your central atom has a octet, all right, satisfies its octet. Now, if we look at carbon, it doesn't have a satisfied octet. And there's a couple of things that we can do and draw out that would be correct. So there are a couple of resonance structures for carbon dioxide that we can draw out. We can form a triple bond between one carbon and oxygen bond, all right, keeping the other carbon-oxygen bond as a single bond. Or we can form a double bond between each carbon-oxygen bond, all right, or we can draw a triple bond between the other carbon and oxygen bond. So we can have something that looks like this. Now, the most significant resonance structure you can figure out by simply accounting for the formal charge of each atom, because all of these structures have atoms with full octets. So then you start to move into the second and third rulings where you try to figure out formal charges and which ones have no formal charges, which ones have formal charges. If they do, where are the formal charges located in terms of atoms? All of that will help you account for which one is the most significant structure. Now, yes, carbon dioxide has these 3 resonance structures, but the one that is the most significant resonance structure is going to be this one. And it's going to be this one because each of these atoms actually has no formal charge. All right, so this resonance structure is going to be the most significant resonance structure. So let's take a look at this. All right, remember that our goal here in this part is to figure out what the character of carbon dioxide as a whole molecule would be. Now, if we have the Lewis structure, the next thing that we want to do is actually go ahead and figure out the geometry of this molecule. In order to do that, we're looking at our central atom, and we need to figure out how many regions of electron density are around this central carbon. This is one region of electron density, and this is another region of electron density. So carbon dioxide has 2 regions of electron density. That means that its structure, according to Vesper theory, is it's going to be a linear geometry for this carbon dioxide molecule. And that means that the way we drew it here is actually pretty appropriate because there is 180 degrees between these bond angles. Now, this is perfect. Why is this perfect? Because it's going to make it really easy for us to determine the net dipole moment. And we need to figure out the net dipole moment if we want to figure out what the character of this whole molecule is. In order for us to figure out the net dipole moment of the whole molecule, we have to figure out the dipole moment of each of these bonds. So looking at this first carbon-oxygen bond right here, oxygen is more electronegative, so it's going to pull the electrons a little bit more towards it. So that's the dipole moment of this bond. What about the other carbon-oxygen bond? Again, oxygen's more electronegative, so it's going to pull the electrons a little bit more towards it. That is the dipole moment for that carbon-oxygen bond. Now, to figure out the net dipole moment, we would be adding these 2 vectors together, but notice that they're in the opposite direction, so if we add them up, they would cancel each other out, and the net dipole moment for this molecule is actually 0. If the net dipole moment is 0, this molecule is non-polar. Otherwise, it would be polar, but the net dipole moment for carbon dioxide is 0. So that means carbon dioxide, the whole molecule, is non-polar. But recognize that's not what the first question asked of us. The first question asked, what is the character of the bonds? And that's why it's really important to focus on what a problem really asks of you. All right, so if it asked us what is the character of the bonds in carbon dioxide, we figured out that these are polar covalent bonds. And then we figured out that if we were to determine the character of the whole carbon dioxide molecule, the two dipole moments from both carbon-oxygen bonds actually cancel each other out, and the molecule as a whole is non-polar. And I know that diverges from the first problem, but I think it's an important lesson and topic to understand nevertheless, so I hope you don't mind that I went on that tangent. But with that, we've solved problem 1. 1 is B. Let's go ahead and move into problem 2. Problem 2 says, which of the following molecules contains the oxygen atoms with the most negative average formal charge? Now, to determine which molecule contains oxygen atoms with the most negative average formal charge, it's going to be important that we understand the concept of formal charge. Formal charge is a charge that's assigned to an atom in a molecule, assuming that electrons in all chemical bonds are shared equally between atoms, regardless of relative electronegativity. And the formula that's used to calculate the formal charge is shown here. It's the total number of valence electrons for that atom minus the non-bonding electrons minus 1/2 the bonding electrons. So what we're going to do is we're going to go through each answer choice and work through them and then figure out which molecule contains the oxygen atom with the most negative average formal charge. So let's start with option A. In water, all right, we have drawn here, in water, oxygen forms 2 single bonds with hydrogen, and it also has 2 lone pairs of electrons. And so we can go ahead and calculate the formal charge for this oxygen. Oxygens have 6 valence electrons, and we're going to subtract from that 6 the number of non-bonding electrons. So we have 2 pairs of lone pairs electrons, so that means we have 4 non-bonding electrons. So we have 6 minus 4 minus 1/2 the number of bonding electrons. We form 2 bonds, all right, and there's 2 electrons per bond, and so that is a total of 4. So what we have here is 6 minus 4 minus 2, and that gives us a charge of 0. So the formal charge on the oxygen atom in water is going to be 0. So let's write that out in purple, and we're going to keep that in mind. Now, the next answer choice is the carbonate ion, CO3 2-. Now, this is really interesting because we have a charge that's associated with the molecule that is given to us in the answer choice. And so we can go ahead, we can draw out this molecule. It actually has a couple of resonance structures, but we notice that there are 3 oxygen atoms that is bonded to the central carbon atom. We have 3 oxygen atoms bonded to a central carbon atom. Now the ion carries an overall charge of 2-. They tell us that in the problem right here just by giving us the molecular formula for the carbonate ion. And so if we draw out the resonance structures we're going to get the same kind of information that's already kind of given to us in the molecular formula that's provided in this answer choice. The resonance structures of carbonate indicate that the negative charge is delocalized over the 3 oxygen atoms. And so this is going to give each oxygen atom an average formal charge of -2 over 3. This is the -2 charge that's associated with the molecule, and the denominator is going to be 3 because it's delocalized over all 3 oxygen atoms, because when we draw the resonance structure, it demonstrates that we can have a double bond here or here, or here. And so the real carbonate ion looks like a blend of all of these. And so those electrons are really just delocalized over this region. And so when you have a molecule like this, the way that you would figure out the formal charge is taking the net charge that's associated with the molecule as a whole and dividing it by the number of atoms that this charge is delocalized over. And so for carbonate here, the average formal charge is going to be -2, the total charge that's associated with the ion, over 3, the 3 oxygen atoms that this charge is delocalized over. All right, so this is our charge, our average formal charge associated with the carbonate ion. Now, answer choice C, this is ozone, O3. Now, we do not see any charge associated with O3. And so your go-to is to draw it out, just like we did with water, right? We had water drawn out, H2O. O3, let's go ahead and draw that out. And what you'll realize, attempting to draw out the Lewis structure for O3, is that you can draw out 2 resonance structures for ozone. And even though there is not a net charge associated with O3, you will soon realize when drawing the resonance structure that there is a positive charge and a negative charge associated with the oxygen atoms, and one has no charge at all. And so yes, the total charge, 0, plus, minus, all cancel out to have a total of no charge on each resonance structure. There is a local charge associated with these atoms. And so that's important to account for. That's important to account for because what we have here, all right, what we have here is a +1 charge at one oxygen atom, a 0 charge at another oxygen atom, and a -1 charge on the third oxygen atom. And so the average formal charge for the oxygen atoms in O3 is going to be -1 over 3, right? Since that one oxygen that has a -1 charge, all right, and the others have 0 and +1 charges, this negative is actually delocalized over this area, all right? And so we account for that -1 charge over the 3 oxygen atoms. And so the average formal charge here is going to be -1 over 3. Okay, fantastic. Now, the last molecule we're given here, this is formaldehyde, CH2O. Let's go ahead and draw it out. It's going to look something like this. You have a carbon double bonded to the oxygen, and also the carbon has 2 bonds to 2 different hydrogens. Now, what we're trying to figure out is the formal charge of the oxygen atom. All right, formal charge of this oxygen atom, well, oxygen has 6 valence electrons. It has 4 non-bonded electrons, -1/2. How many bonded electrons does it have? Well, it has 2 bonds to carbon for a total of 4 bonded electrons. And so this is also going to give us 0. The formal charge associated with this oxygen is 0. So what we have here is, let's write them out for each answer choice, 0 and 0 for A and D. Then we have -2 over 3 for answer choice B, and -1 over 3 for answer choice C. Comparing the formal charges, the oxygen atoms in the carbonate ion have the most negative average formal charge of approximately -2 over 3. That'll be like about 0.67, -0.67. And so the correct answer here is going to be B. 2 is B. Let's do problem 3 next. Problem 3 says, which of the following elements does not break the octet rule? Our answer choices are beryllium, sulfur, sodium, and phosphorus. Now, to determine which element among these given options doesn't break the octet rule, it's important that we remember what the octet rule is. The octet rule states that atoms tend to form bonds until they are surrounded by 8 valence electrons, achieving a stable electron electron configuration that's similar to that of noble gases. However, in our lecture, we discussed that there are several exceptions to this rule, often involving elements with fewer or more than 8 electrons in their valence shell. The 3 exceptions that we covered is 1, incomplete octet. There are elements that are stable with fewer than 8 electrons in their valence shell, and they include hydrogen, helium, and lithium, which are all happy and stable with 2 valence electrons, beryllium, which is stable with 4, and boron, which is stable with 6 valence electrons. The second rule was the expanded octet. Any element in period 3 and greater, can have more than 8 electrons. This includes phosphorus, which can have up to 10 valence electrons, sulfur with up to 12, chlorine with up to 14, and there are many more examples of this. The last rule is odd number of electrons. Any molecule with an odd number of valence electrons is not going to be able to distribute those electrons to give 8 to each atom. Now, with this refresher, let's go back to our answer choices and let's work through this one by one. Beryllium, this is an alkaline earth metal. It has an atomic number of 4, and that means it has 2 electrons in its outer shell. Now, beryllium often forms compounds where it will only have 4 valence electrons. And so beryllium actually does not follow the octet rule as it is stable with 4 valence electrons, which is fewer than 8 in its valence shell. And so beryllium is actually an exception to the rule. That's not what we're looking for. We're trying to figure out which one of these answers does not break the octet rule. Beryllium does, as it is stable with only 4 valence electrons. Okay, what about sulfur? Sulfur has an atomic number of 16. It's in group 16 of the periodic table, and it has 6 valence electrons. Now, sulfur can follow the octet rule in many compounds, but sulfur can also expand its valence shell to hold more than 8 electrons. Sometimes sulfur can hold up to 12 even valence electrons. And so that means while sulfur can follow the octet rule, it can also break the octet rule depending on the compound. So that's also not what we're looking for. We're trying to figure out which element does not break the octet rule. Next up, we have sodium. Sodium is an alkali metal with an atomic number of 11, giving it 1 valence electron. In a lot of chemical reactions, sodium tends to lose this electron to form sodium plus ion, achieving a noble gas electron configuration with 8 electrons in its outer shell. Now, since sodium achieves an octet by losing its valence electron, sodium is one of those atoms that actually does not break the octet rule. So this is good. This is what this problem is asking for. But still, let's talk about our last answer choice, phosphorus. Phosphorus has an atomic number of 15. It's in group 15 with 5 valence electrons. And while phosphorus can follow the octet rule, it can also exceed the octet rule, and it can house up to 10 valence electrons. And so again here, it can follow, but it can also break the octet rule. So that's not what we're looking for. So connecting this information back to the question, we're looking for an element that does not break the octet rule, and the answer here is going to be sodium. Sodium does not break the octet rule. 3 is C. Let's go ahead and do problem 4. Problem 4 says, which of the following correctly ranks the compounds below by ascending boiling point? We have acetone, potassium chloride, krypton, and isopropyl alcohol. Now, to determine which option correctly ranks the given compounds by ascending boiling point, it's going to be important to understand the factors that influence boiling points. Boiling points are affected by the kind of bonding that's occurring in a molecule and by intermolecular forces like hydrogen bonding, dipole-dipole interactions, and London dispersion forces. One note to remember is that ionic bonds are much stronger than covalent bonds and thereby significantly stronger than any type of intermolecular force that's present in molecular compounds. Keeping that in mind, let's go ahead and work through each of these compounds and discuss what kind of forces are at play. So starting off with acetone, I'm going to go ahead and draw what acetone looks like. Acetone has this carbon that is double bonded to an oxygen, and then that carbon is bonded to carbons, all right, on both sides here, and these carbons all have 3 hydrogens. So these are methyl groups at the end. So this is what acetone looks like. Acetone is a polar molecule with a significant dipole moment due to the carbonyl group. It exhibits both dipole-dipole interactions as well as London dispersion forces, but it does not engage in hydrogen bonding because it lacks a hydrogen atom that's actually attached to a highly electronegative atom like oxygen, nitrogen, or fluorine. All right, so keeping that in mind, it probably has a moderate boiling point, but we don't know what we're comparing it to just yet. So we'll keep that in mind. For acetone, dipole-dipole London dispersion forces. Okay, what about potassium chloride? Potassium chloride, this is an ionic compound that's composed of potassium and chloride ions. And remember that ionic bonds are much stronger than covalent bonds and significantly stronger than any type of intermolecular force that's present in molecular compounds like we saw in acetone. And so consequently, potassium chloride is going to have a very high boiling point due to the strong electrostatic forces between the ions. All right, then we have krypton. All right, krypton is a noble gas. As such, it is a non-polar atom. The only intermolecular forces that krypton atoms experience are going to be London dispersion forces. All right, and that's going to be the weakest type of intermolecular force. So krypton probably has a very low boiling point. And then our last molecule is isopropyl alcohol. So let me also go ahead and draw that out for you. You have carbon that's bonded to an oxygen that's bonded to a hydrogen. And then this carbon is also bonded to 2 carbons. Each of these carbons have 3 hydrogens. These are methyl groups at the end as well. All right, so looking at this, isopropyl alcohol, it can actually form hydrogen bonds due to the presence of this OH group right here. Hydrogen bonding, as a reminder, is a strong intermolecular force. It's stronger than dipole-dipole interactions, and it's also stronger than London dispersion forces. All right, but generally weaker than ionic bonds. So that's an important thing to keep in mind. And so isopropyl alcohol has probably a relatively high boiling point compared to acetone and krypton, but lower than ionic compounds like potassium chloride. So based on the analysis of these molecules and their intermolecular forces, or these compounds and their intermolecular forces, we can begin to rank the compounds by boiling point. Remember that the weakest intermolecular forces result in the lowest boiling point, and the strongest forces result in the highest boiling point. And so here is the order, all right, here is the order from, or here is the order by ascending boiling point, all right, from lowest to highest. The lowest boiling point is going to be probably from krypton because it only has London dispersion forces. Now this is assigned statement 2. All right, we want to keep that in mind because the answer choices are ranking them based off of their numbers. All right, the second one, all right, second after krypton for higher boiling point is probably going to be acetone. Acetone has dipole-dipole interactions and London dispersion forces. So krypton has the lowest, then acetone has a slightly higher boiling point. That's statement 1. After that is probably going to be isopropyl alcohol because it has hydrogen bonding, which is the strongest of the intermolecular forces. And then the one that has the highest boiling point is going to be potassium chloride because potassium chloride is an ionic compound. And so we're looking for an answer that writes, okay, that writes specifically in this order 3 followed by 1, followed by 4, followed by 2. All right, and I wrote krypton wrong. This is supposed to be 3. All right, so 3 followed by 1, followed by 4, followed by 2. That's going to be answer choice D, and we can double check. 3 is krypton. That's correct. It has the lowest boiling point. 1 is acetone. That's true. That follows it. It has a slightly higher boiling point than krypton, followed by statement 4, which is isopropyl alcohol, and the one with the highest boiling point is potassium chloride. All right, so the answer to problem 4 is going to be D. Let's move on to problem 5. Problem 5 reads, both carbonate and chlorine trifluoride have 3 atoms bonded to a central atom. What is the best explanation for why carbonate has trigonal planar electronic geometry, while chlorine trifluoride has trigonal bipyramidal electronic geometry? To be able to answer this question, we need to recall our principles of electronic geometry and Vesper theory. This theory helps predict the shape of molecules based on the repulsions between electron pairs around a central atom. So first, let's understand the structures and electron arrangements of both carbonate and chlorine trifluoride. Now, earlier we saw and discussed carbonate ion in a previous question. We saw that it has a couple of resonance structures, but we're not going to concern ourselves too much about the resonance structures. We just need to draw one to get the gist. So the carbonate ion, it consists of a carbon atom, a central carbon atom that's bonded to 3 oxygen atoms. So it looks something like this: carbon bonded to 3 oxygen atoms. All right, and we saw that for the resonance structures, you can draw a double bond here, you can also draw a double bond here, and you can draw a double bond here, but really those electrons are delocalized, so it looks something like this. This is the main point that we want to draw here. What we can recognize here is that carbon has a satisfied octet, and what it has is 3 regions of electron density. The carbonate ion has 3 regions of electron density, and for 3 regions of electron density, the electronic geometry is going to be trigonal planar. Now, chlorine trifluoride, this is different because we have a central chlorine atom that's bonded to 3 fluorine atoms, but it will also have 2 pairs, all right, 2 lone pairs of electrons on that central atom. So in this chlorine trifluoride molecule, there are 3 bonding pairs, 1 for each chlorine-fluorine bond, and then there are 2 lone pairs on the chlorine atom. And so according to Vesper theory, for this molecule, we have 5 regions of electron density. And when you have 5 regions of electron density, the electronic geometry is going to be trigonal bipyramidal. Okay, keeping that in mind, let's go ahead and work through the answer choices now that we know this. The first answer choice says carbonate has multiple resonance structures, while chlorine trifluoride does not. And while it is true that carbonate has multiple resonance structures, resonance does not determine the basic electronic geometry, which is going to be predicted by Vesper theory based on electron pairs, based off of regions of electron density. So A is not really a good explanation for why carbonate and chlorine trifluoride have different electronic geometries. Answer choice B says carbonate has a charge of -2, while chlorine trifluoride has no charge. The charge on a molecule can influence its overall stability and reactivity, but again, it does not directly determine the electronic geometry. The geometry is based on electron pair repulsions, okay? That is so important. The geometry is based on electron pair repulsions. So that's not a really good answer either. So not B. C says chlorine trifluorine or trifluoride has lone pairs on its central atom, while carbonate has none. This statement correctly addresses the difference in electron pair arrangements that directly influence the electronic geometry. Chlorine trifluoride has 2 lone pairs on the central chlorine atom, which results in a trigonal bipyramidal electronic geometry, while carbonate has no lone pairs on the central carbon atom, resulting in a trigonal planar geometry. So even though both of these molecules have 3 bonds, those lone pairs on chlorine trifluoride results in that molecule having a completely different electronic geometry than carbonate. All right, let's look at answer choice D still. It says carbonate has lone pairs on its central atom while chlorine trifluoride has none. This statement is just outright incorrect. Carbonate does not have any lone pairs on the central atom. And so with all of that being said, the correct answer for 5 is going to be C. Wonderful. Let's move on to problem 6. Problem 6 says, which of the following elements, when paired together, would form ionic bonds? To determine which pair of elements form ionic bonds, we need to understand the nature of ionic bonding. Ionic bonds occur when one atom donates one or more electrons to another atom, resulting in the formation of oppositely charged ions that are attracted to each other. Now, this typically happens between metals and nonmetals due to their differences in electronegativity. Now, we're going to use the difference in electronegativity to find a pair of elements that would form an ionic bond. So let's work through our answer choices. Answer choice A says element 2 and 4. Element 2 is chlorine and element 4 is hydrogen. So we're going to take the electronegativity difference between chlorine, which is 3.2, and hydrogen, which is 2.2, and that gives us a difference of 1. Now, a difference in electronegativity of 1 falls in the range of polar covalent bonding. So this is not going to be an ionic bond. So A is not the correct answer. B says element 1 and 2. Element 1 is magnesium, and element 2 is chlorine. So let's take the difference between the electronegativity values of magnesium, which is 1.3, and chlorine, which is 3.2. 3.2 minus 1.3 is going to be equal to 1.9. 1.9, this is in the range of ionic bonding. Any electronegativity difference of 1.7 and greater means that these two elements are going to form an ionic bond. So magnesium and chlorine are going to form an ionic bond. And this makes sense because magnesium is a metal and chlorine is a non-metal. And ionic bonding typically happens between metals and non-metals. So B is correct, but we're going to work through the rest of these answer choices. C says element 2 and 3. Element 2 is chlorine, element 3 is oxygen. If we take the electronegativity difference, 3.5 minus 3.2, we get a difference of 0.3. This falls in the range of non-polar covalent bonding, not ionic bonding, so C is also not the correct answer. Answer choice D says element 3 and 4. Element 3 is oxygen, element 4 is hydrogen. If we take the difference in electronegativity, 3.5 minus 2.2, that gives us a difference of 1.3. This falls in the range of polar covalent bonding. And that's not the answer because we're looking for a pair of elements that would form ionic bonds. And that's going to be answer choice B for problem 6. With that, we're going to move into problem 7. Problem 7 says, despite the fact that both acetylene and hydrogen cyanide contain triple bonds, the lengths of these triple bonds are not equal. Which of the following is the best explanation for this finding? Now, to be able to answer this question, we need to understand the factors that influence bond length. Bond length is affected by the size of the atoms involved and the nature of the bonds, including their electronegativity. So let's start by looking at the structures and bonding in both acetylene and hydrogen cyanide. So let's start with acetylene, C2H2. This is a molecule where 2 carbon atoms are going to be connected by a triple bond, and each carbon is also bonded to a hydrogen atom. So this is what this molecule looks like. Now, the triple bond in acetylene consists of 1 sigma bond and 2 pi bonds. Remember, we went over this near the end in our lecture. We said single bonds are sigma bonds, double bonds are 1 sigma bond, 1 pi bond, and triple bonds are 1 sigma bond, 2 pi bonds. So this is a triple bond. Therefore, it is 1 sigma bond and 2 pi bonds. Now, since the bond is between 2 carbon atoms of the same element, they both have the same electronegativity, and there's no significant difference in the electron density distribution. Okay, now let's look at hydrogen cyanide, HCN. In this structure for hydrogen cyanide, we have a carbon atom that is triple bonded to a nitrogen atom and single bonded to a hydrogen atom. Now, the triple bond in hydrogen cyanide also consists of 1 sigma bond, 2 pi bonds. However, unlike in acetylene, the triple bond here is between a carbon and a nitrogen, which have different electronegativities. Nitrogen is more electronegative than carbon, and so it's going to pull the shared electrons more towards itself, leading to a different bond character compared to the acetylene triple bond. With that in mind, we're going to go back and we're going to work through these answer choices one by one. A says in acetylene, the bond is shorter because it is between atoms of the same element. Now, this statement implies that the equal sharing of electrons and the similar size of the carbon atoms is going to result in a shorter bond length. But since the two atoms involved are identical, the bond length is influenced by this symmetry and by uniform electron distribution. Okay, now considering this, that does not seem to be the best explanation for this finding. Let's work through answer choice B. The two molecules have different resonance structures. Well, resonance structures describe different ways of representing the electron distribution in a molecule, usually leading to a hybrid structure. However, in both of these molecules, the triple bond is a straightforward single representation with no significant resonance contributing structures that is going to affect the bond length in a major way. So this is not a correct explanation for the difference in bond lengths. All right, so far, A and B are not correct. Let's go to C. C says carbon is more electronegative than hydrogen. Okay, this is a true statement on its own, but it does not directly explain the difference in triple bond lengths because the triple bonds is not happening between the hydrogen and the carbon. The triple bond is happening between carbon and carbon for acetylene and carbon and nitrogen for hydrogen cyanide. D says nitrogen is more electronegative than carbon. Now, this statement correctly identifies the difference in electronegativity between carbon and nitrogen. Nitrogen being more electronegative pulls the shared electrons in the triple bond closer to itself, and that's going to lead to a bond that is slightly shorter and stronger compared to the bond between the two carbon atoms where electrons are just shared equally. And so the correct answer here for 7 is going to be D. Fantastic. Moving on to problem 8. Problem 8 says, which of the following is the best explanation of the phenomena of hydrogen bonding? All right, so to determine that, let's just go over hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction that occurs when a hydrogen atom is covalently bonded to a highly electronegative atom, like nitrogen, oxygen, or fluorine. Now, the significant electronegativity difference, it creates a polar bond with a strong partial positive charge on the hydrogen atom and a partial negative charge on the electronegative atom. In hydrogen bonding, that partially positive hydrogen atom from one molecule is attracted to the lone pair of electrons on the electronegative atom of a neighboring molecule. And this interaction is stronger than typical dipole-dipole interactions due to the high polarity of the bond, but it is weaker than covalent or ionic bonds. Keeping that in mind, let's go through the answer choices, all right? One by one. A says hydrogen has a strong affinity for holding onto valence electrons. This statement is incorrect because hydrogen bonding is not about hydrogen holding onto valence electrons strongly. Instead, it's about the hydrogen atom, when bonded to an electronegative atom, being partially positive and then being attracted to lone pairs on another electronegative atom. So A does not answer this problem properly. Okay, what about B? B says hydrogen can hold only 2 valence electrons. Again, this is a true statement, all right, but it doesn't explain hydrogen bonding. The limitation of hydrogen's valence shell capacity is not directly related to the formation of hydrogen bonds. So we have to be careful maneuvering these kinds of problems because they'll make correct statements, but they're not the proper explanation for certain phenomena. Looking at answer choice C, C says electronegative atoms disproportionately carry shared electron pairs when bonded to hydrogen. Now, this statement correctly captures the essence of hydrogen bonding. When hydrogen is bonded to an electronegative atom, the shared electrons are pulled closer towards the more electronegative atom, and that creates a partial positive charge on the hydrogen and a partial negative charge on that electronegative atom. All right? This partial positive charge on hydrogen is then strongly attracted to the lone pairs of electrons on neighboring electronegative atoms. That is what causes this intermolecular force, this hydrogen bond. Now, C is fantastic, but let's read D anyways. D says hydrogen bonds have ionic character. Okay, that is just outright false. That is not a true statement, right? Hydrogen bonds, they do not have ionic character. Ionic bonds involve the transfer of electrons and the formation of charged ions, whereas hydrogen bonds are purely electrostatic interactions between partial charges on polar molecules, like we see here, right? We have this partial positive charge on a hydrogen that's bonded to an oxygen, and then this hydrogen goes out and has a hydrogen bonding electrostatic interaction with another water molecule, but the oxygen atom that has that partial negative charge. All right, so the correct answer then for 8 is going to be C. Moving on to problem 9. Problem 9 says, which of the following best describes the number and character of the bonds in an ammonium cation? So to determine this, we need to understand the structure and binding in this ion. The ammonium ion, which is NH4+, is derived from ammonia, NH3, by the addition of a proton. Okay, keeping this in mind, let's start from the beginning. Ammonia, so NH3, let's start from there. NH3 has a trigonal pyramidal structure with nitrogen that's bonded to 3 hydrogens and has a lone pair. All right, and this nitrogen-hydrogen bond, these are polar covalent bonds. Now, when ammonia accepts a proton, all right, an H+, all right, the lone pair on the nitrogen atom forms a bond with the proton, resulting in the formation of the ammonium ion. And so then in the ammonium ion, nitrogen is at the center, forming 4 bonds with 4 hydrogen atoms. The addition of the proton then results in 4 regions of electron density around the nitrogen, fun fact, leading to a tetrahedral geometry. Now, each hydrogen atom is connected to the nitrogen atom through a covalent bond. All right, so keeping that in mind, let's just remind ourselves of a couple of things. Covalent bond. A covalent bond is formed when 2 atoms share a pair of electrons. So in ammonium, nitrogen forms covalent bonds with the 4 hydrogens. Okay, polar covalent bonds. Since nitrogen is more electronegative than hydrogen, the shared electrons in this NH bond are more attracted to the hydrogen atom, making these bonds polar covalent. Now, as a reminder, what about coordinate covalent bonds? A coordinate covalent bond is a type of covalent bond in which both shared electrons come from the same atom. So in ammonium, in the ammonium cation, one of those NH bonds is actually formed when the lone pair of electrons on nitrogen in ammonia, all right, donates those electrons to a proton, H+. And so this bond is a coordinate covalent bond. So then with that information, let's consider some of these answer choices. A says that we have 3 polar covalent bonds. Remember, the question is asking what best describes the number and character of the bonds in this ammonium cation. A says 3 covalent bonds, 3 polar covalent bonds. That's not true. The ammonium ion has 4 bonds, not 3. So A is incorrect. B says 4 polar covalent bonds, of which none are coordinate covalent bonds. Now, this choice does correctly identify the number of bonds as 4 and that they're polar, but it incorrectly states that none are coordinate covalent bonds. That's not true. In the ammonium cation, one of the bonds is indeed a coordinate covalent bond. C says 4 polar covalent bonds, of which one is a coordinate covalent bond. This choice correctly identifies the ammonium cation, all right, has 4 polar covalent bonds, and it correctly states that one of these bonds is a coordinate covalent bond. This answer choice is correct. Just going through D as well, 4 polar covalent bonds, of which 2 are coordinate covalent bonds. This is incorrect. There's not 2 coordinate covalent bonds. So the correct answer for 9 is going to be C. Wonderful. Let's move on to problem 10. Problem 10 says, although the octet rule dictates much of molecular structure, some atoms can violate the octet rule by being surrounded by more than 8 electrons. Which of the following is the best explanation for why some atoms can exceed the octet? To determine why some atoms can exceed the octet rule, it's essential to understand the basic principles of electron configuration and molecular structure. Remember that the octet rule states that atoms tend to form bonds until they're surrounded by 8 valence electrons, and that helps them achieve a stable electron configuration similar to that of noble gases. However, there are exceptions to the rule, particularly for elements in the 3rd period and below, or n equals 3 and greater. All right, so then keeping that in mind, let's go through these answer choices. A says atoms that exceed the octet already have 8 electrons in their outermost electron shell. Now, this statement is correct. Atoms that exceed the octet rule do so by accommodating more than 8 electrons in their valence shell, not because they already have 8 electrons. B says atoms that exceed the octet only do so when bonding with transition metals. Now, the statement isn't entirely accurate. While transition metals themselves often have more than 8 electrons due to their d orbitals, non-transition metals like sulfur, phosphorus, and chlorine can also exceed the octet rule without bonding to transition metals. We've discussed this already in this video and in the lecture video when we went over some of the exception rules for the octet principle. So B is not correct. C says atoms that exceed the octet do so because they have d orbitals in which extra electrons can reside. Now, this statement is true. Atoms in the 3rd period and beyond have d orbitals that are available in their valence shell, allowing them to accommodate more than 8 electrons. That is the correct statement, but let's read D. D says some atoms can exceed the octet because they are highly electronegative. This statement is incorrect. Electronegativity is a measure of an atom's ability to attract electrons, but it does not explain the ability to exceed the octet. The capacity to exceed the octet is related to the availability of additional orbitals, specifically d orbitals. So the correct answer for 10 then is C. Let's move on to problem 11. Problem 11 says, which of the following types of intermolecular forces provides the most accurate explanation for why noble gases can liquefy? Now, noble gases are a group of elements in group 18 of the periodic table. These gases are characterized by their full valence electron shells, which make them chemically inert and nonpolar. Since noble gases are nonpolar, they're not going to form hydrogen bonds and they're not going to have dipole-dipole interactions under normal conditions. Now again, since noble gases are nonpolar and chemically inert, the only significant intermolecular force acting between noble gas atoms is dispersion forces. Dispersion forces, also known as London dispersion forces, are the result of temporary dipoles that occur when electrons in an atom or molecule are unevenly distributed at any given moment. And these temporary dipoles induce corresponding dipoles in neighboring atoms or molecules, leading to weak attractions. So the correct answer for problem 11 is going to be C, dispersion forces. This is the only intermolecular force that noble gases can partake in. With that, we move into problem 12. Problem 12 says, in the structure shown, which atom or atoms have the most positive charge? Now, in order to answer this problem, we're going to have to analyze the distribution of charges in this phosphate ion. And to do that, we're going to have to calculate the formal charge on the phosphorus atom and on each oxygen atom. So let's go ahead and start with the formal charge for phosphorus. Remember, formal charge is the number of valence electrons, which is 5 for phosphorus, minus the number of non-bonding electrons or lone pair electrons. Phosphorus has 0, minus 1/2 the number of bonding electrons. Phosphorus participates in 4 single bonds with oxygen atoms. 2 electrons per bond gives us a total of 8 bonding electrons. So what we have here is 5 minus 4, and that gives us a +1 charge on our phosphorus atom. Now, each of these oxygens is equivalent, so we really just need to calculate the formal charge for one of them, and it's going to be the same for all 4. Same thing, valence electrons for oxygen at 6, minus lone pairs, all right, non-bonding electrons. Each oxygen atom has 6 of those, minus 1/2 multiplied by the number of bonding electrons. Each oxygen participates in 1 single bond with phosphorus, so that is 2 total electrons. If we calculate this for oxygen, it's 6 minus 6 minus 1, so each oxygen atom actually has a charge of -1. Now, given that the overall charge of the ion is -3, everything adds up, right? Our charge for our phosphorus is +1, and then we have a -1 charge for each of the 4 oxygens. So -1, -1, -1, -1, and that gives us a total charge of -3. So that checks out, which means we did the formal charge calculations appropriately. Then it becomes really obvious which atom has the most positive charge. It's phosphorus, which means that the correct answer for 12 is going to be A. Let's move on to problem 13. Problem 13 says, which of the following is the best name for the new bond that is formed in the reaction shown? All right, so this is really good. Let's look at this. So what we have, all right, the reaction in this question, it shows water, and water molecule has 2 lone pairs, all right, on that central oxygen, and it's combining with a free hydrogen cation. The resulting molecule is a hydronium ion, H3O+, and this is formed from the new bond between that hydrogen ion, all right, between that proton essentially, that free hydrogen cation, and the water molecule. Now, how was this bond created? This bond is created via the sharing of one of oxygen's lone pairs with this free hydrogen ion. This represents the donation of a shared pair of electrons from that water molecule to that proton. This type of bond is called a coordinate covalent bond. And so the correct answer for problem 13 is going to be C. Wonderful. Let's move on to problem 14. Problem 14 says both boron trifluoride and ammonia have 3 atoms bonded to the central atom. Which of the following is the best explanation for why the geometry of these 2 molecules is different? Now, this is very similar to a problem that we did earlier. And the thing that we have to rely on here is Vesper theory. So according to Vesper theory, the shape of a molecule is determined by the number of bonding pairs of electrons and lone pairs of electrons around the central atom. Electron pairs repel each other, and so they try to adopt an arrangement that minimizes these repulsions, and that determines the geometry of the molecule. So let's work through the geometry of boron trifluoride and ammonia. Boron trifluoride has a central boron atom with 3 fluorine atoms bonded to it. Boron has 3 valence electrons and it forms 3 single bonds with fluorine atoms using all its valence electrons. Now, there are no lone pairs on the boron atom, and it is okay that it doesn't have a complete octet because boron is one of those exceptions. Boron is happy with 6 valence electrons. Now, according to Vesper theory, this boron atom has 3 regions of electron density around it. And so that means the expected electronic geometry is trigonal planar. Okay, now keeping that in mind, let's work through ammonia next. Ammonia has a central nitrogen, and it has 3 hydrogens bonded to it. Now, nitrogen has 5 valence electrons, 3 that are used to form single bonds with hydrogen atoms, and that means that the remaining 2 electrons form a lone pair. So nitrogen actually is surrounded by 4 regions of electron density, which means that the electronic geometry is that of a tetrahedral. Okay, so keeping that in mind, let's work through our answer choices. A says boron trifluoride has 3 bonded atoms and no lone pairs, which makes its geometry trigonal pyramidal. Okay, now this statement is incorrect. It does have 3 bonded atoms and no lone pairs, but that makes it have a trigonal planar geometry, not trigonal pyramidal. Okay, so not A. B says ammonia is nonpolar while boron trifluoride is polar. Okay, the statement is also incorrect. In fact, boron trifluoride is nonpolar due to its symmetric trigonal planar shape, which causes the dipoles to cancel out. Ammonia, on the other hand, is polar because its trigonal pyramidal shape results in a net dipole moment. So not B either. C says ammonia has 3 bonded atoms and 1 lone pair, which makes its geometry trigonal pyramidal. Now, this statement is true. All right, the statement is correct. Ammonia does have 3 bonded atoms and 1 lone pair, and that does give it a trigonal pyramidal geometry due to the repulsions between the lone pairs and the bonding pairs. So that statement is correct. D says boron trifluoride is nonpolar while ammonia is polar. Now, this statement is true about the polarity, but again, it doesn't address the primary reason for the difference in their geometries. The polarity of the molecule is a consequence of their geometries, not a cause. And so the correct answer for 14 is going to be C. Now we can move on to our last and final problem. Problem 15 says, which of the following compounds has the highest melting point? Is it sucrose, sodium chloride, glycerol, or water? Now, to determine which compound has the highest melting point, we need to consider the types of bonding and intermolecular forces that is present in each substance, because the strength of these interactions is going to directly affect the melting point. Now, the melting point is the temperature at which a solid becomes a liquid, and substances with stronger intermolecular forces or ionic bonding generally have higher melting points because more energy is required to overcome these interactions. So let's go over our answer choices. First answer choice is sucrose. Sucrose is a sugar. It's a large molecular compound that has multiple hydroxyl, this is OH groups, and this allows for extensive hydrogen bonding. Okay, so that's something that we need to keep in mind with sucrose. There's hydrogen bonding. However, something to keep in mind is that it is a covalent compound, and so the intermolecular forces like hydrogen bonding, it's not as strong as ionic bonding, and we should keep that in mind. Okay, next up is sodium chloride. This is an ionic compound with strong electrostatic forces between the sodium cation and the chloride anion. These ionic bonds are very strong and they require a significant amount of energy to break. Okay, so this is ionic. We need to keep that in mind, ionic bonding. All right, answer choice C is glycerol. Glycerol, this has 3 hydroxyl groups. These are OH groups. And I have sucrose here and glycerol here just so you can visualize what I mean when I say they have a lot of OH groups. And this, again, leads to significant hydrogen bonding. Now, again, hydrogen bonds are strong, but they're not as strong as ionic compounds. And then our last answer choice is water. Water is known for its strong hydrogen bonding due to the 2 hydrogen atoms bonded to oxygen. But again, while hydrogen bonding is the strongest intermolecular force, it's not as strong as ionic bonding. And there's only one answer choice here that demonstrates an ionic compound, and that is sodium chloride. All right, so again, in sodium chloride, these interactions are ionic, and it's going to have a higher melting point. It's going to have the highest melting point in comparison to the other answer choices. And so the correct answer for 15 is going to be B. I really hope that this was helpful. We have completed all our practice problems for today. Let me know if you have any questions, comments, concerns. If you want further explanation on any of these problems, I am more than happy to provide that. Just let me know. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.